I'm excited to be back in Atlanta to visit with Dr. Brian Beck and ask him how he's using TIMS to teach students in his lab.
So the question is, first question, why is this topic, equalization, important for students? I think my answer there would be that, of course, the function of an equalizer is very important because, like it or not, in most communication systems, one would need to use an equalizer to make up for the effects of the channel to avoid unacceptably high bit error rates or something that would require you to communicate unnecessarily slowly if you chose not to use an equalizer. So the importance of it is of course there, but the theory of equalization is pretty inaccessible, I think, to most undergraduate students. And so if one is not able to fully comprehend all of that, well, with the EMONA system, we can implement an equalizer in the hardware, and the students can see the inputs to the system, the effects of the channel, and then the effects of the equalizer, and the results at each step, and how the equalizer has a benefit to the signal. And so even if one doesn't fully understand all of the theory, you can see the results of it right in front of your eyes. And so I think there's a lot of value there to doing it hands-on.
Interesting.
So I think that's my answer for number one.
Okay.
So something it's important to know, even if a lot of the details might be out of reach.
Okay.
Why not use simulation or videos? I think those are options when you're trying to teach something, but there's something to be said about putting together a system with your hands and then viewing the results. And I think that it's unique. It's a unique experience to be in a lab setting and to have the ability to the satisfaction of building something and then watching it work. And since software, for simulations, for example, are used so frequently, I think students are used to doing that. What they're less used to doing is building things in hardware. So I think there's a lot of value to that.
Yep. Sometimes, do you find that sometimes software seems like magic? Things just happen mysteriously?
Sure. Or software might feel like it's not really real, or like it doesn't really represent the physical world necessarily, because of course, if you're doing everything in software, then you are simulating some aspect of reality, right? Some aspect of the hardware. Whereas if we're trying to study the physical layer of communications, then it makes sense that you would want to use a physical thing. And so it's very helpful to be able to do that in the lab.
Yep. Yep.
To really emphasize the physical in terms of the physical layer. You work with actual electrical signals as opposed to computer code, ones and zeros, where everything lives inside a computer. How do the benefits of hands-on learning outweigh the challenges of making mistakes, frustration, etc.? I think that there's just a lot to be said for learning how to debug. So honing your debugging skills, being able to build something physically in the lab. I've taught many lab courses here at Georgia Tech, and while students may get frustrated along the way, it's when you finally get something working at the end that there's a tremendous sense of satisfaction that's involved there. And also that facilitates your learning, because that satisfaction at the end really reinforces what you learned along the way in a way that, let's say, studying for an exam might not.
Yep.
We're satisfied when we get good grades, but there's a different kind of satisfaction associated with building things and seeing them work. And also, again, emphasize that debugging skills. It's hard to learn that outside of labs, in my experience.
Especially for engineers.
Indeed.
Yeah.
I would think that an engineer would need to be proficient in that
Yeah.
after they graduate. what feedback do students give after implementing this complex multi-stage experiment? I think that's a good follow-up to the previous question, which is that generally what they tell me is that like it was a lot of wires and it was a lot of building and there was a reasonable amount of debugging, but once you get to the end, you got to see it working, and that sort of made it all worthwhile and made it seem interesting to them. And so I think it's memorable in that sense.
I imagine it's fairly confronting for them at times, when they're halfway through it and they may have made a mistake somewhere. That it reminds them that they have to be systematic and
I tell them,
get real.
Yes, I have to tell them even in the experiment and then verbally while we're working together is you need to check each step of the way that your subsystem or your block, whatever you're looking at, is working. So what is the expected, given some expected inputs, what is the expected output? So verify that this piece works, and then verify that this other piece is also working, so that when you connect them together, you can expect that it will also work. Because the more things you string together, the more possibilities there are for mistakes. What topics or experiments do not benefit from hands-on? I don't know that there's anything that wouldn't benefit from having a hands-on component, but it's possible and even likely that there are many things that are just very difficult to convert into a hands-on experience. So I think that there's probably a lot of components to my lecture courses and other theoretical treatments of various topics that just don't lend themselves very well to experiments, or that they would be too difficult or cost prohibitive. So the situations like that would not, it's not that they wouldn't benefit, it's just that you'd never get there. You'd never get to the point where you are implementing it as hands-on. So that's a challenge, or maybe other situations where you just can't think of a good experiment. It takes a lot of time and effort to develop an experiment, even with the unique hardware that we've been using here at Georgia Tech, and so that's a cost that you have to pay. You have to be able to have time and energy to develop these things.
Yep.
So that's a hurdle.
And in fact, in my experience, in my travels visiting universities around the world, literally none of them actually have hands-on experiments in signals and systems. They all typically do chalk and talk on the board or simulations, and yet you've been able to, with this experiment, implement hands-on equalization and filter creation in hardware. So I think I honestly feel some people would be surprised to see that's possible, but the benefits are high.
But once you've seen it, then I think people would probably agree that there's a benefit there.
Yeah,
Definitely.
Like I personally was thrilled to see the equalization, see that signal fall apart and then actually be recovered.
It seems like it would be impossible, right?
Yeah, theoretically it's possible in pulse responses and convolution, blah blah. But to see it actually happen under my control was pretty cool.
Yeah, glad you liked it.
Cool.
Well, I thought this was a good set of questions, and I thought that was an interesting discussion.
Thank you.